Let's try some of these transcendental functions, these logs and exponentials and things like that, where we're not just dealing with polynomials all the time. Okay, what about this one? What's the domain? And why? Type it in. What's the domain of that? All reals? Okay, how come, Seth? You're right.
X, well, I mean, there's nothing that could really go wrong. X squared can never be undefined if you put a real into it, and then e is a constant, so e to the negative 2x is just e to some power. So then that's never going to be wrong.
Okay, that's a good way of thinking about it. Nothing bad can happen, right? If we're plugging, there's no value of x we could ever plug in here that's going to cause something to be undefined, right? Another way we could maybe look at this real briefly, let's think about what let's look at this function, e to the minus 2x, for just a second. This is a good opportunity for a little bit of review. So if we take the function y equals e to the x, remember what that looks like, right? That's just going to be that function. Agreed? Okay, so what if I multiply the x by 2? What's that doing? Well, if I multiply the x by 2, it's just, all that's going to do is make the exponents bigger faster, right? If I plug in an x value, I'm going to double that exponent. So it's just going to make this thing steeper. Just going to be the same shape, but it's just going to be slightly steeper, right? Doesn't change things a ton, though. Well, what if I plug in a negative there? Think what this means in terms of transformations, right? Let me just make this a 2x too. Anytime that I multiply, and e to the negative 2x is the same thing as e to the 2 times negative x, right? Aren't I effectively just multiplying the input value by negative 1 there? Would everybody agree? Right? That's the same thing as saying e to the 2 times negative x. So I'm just replacing the x with a negative x, multiplying the x by negative 1. Same thing, right? What does that do in terms of a transformation? If I multiply a function by a negative, it reflects it over the x-axis. Andy, what's it do if I multiply the input value x by a negative 1?
It's the same thing as like 1 over x to the 1.
Well, true, but what's it do to the graph is what I want to know.
Is it like, as the x gets larger, does it get way smaller or something?
It does. Okay, but I just want to know in general, what's it do? Like if I've got some function f of x and g of x equals f of negative x, if I multiply the input by negative 1, what's that doing?
So does it like asymptote out at the y equals 0?
No, but can't you control your dog?
No, I can't.
Anybody else want to weigh in on that? What's it do? Going back to honors algebra 2, what did we say about that? It reflects it over the y-axis is all it does. Okay? We don't use that reflection very often, but that's a good one to be reminded of, right? This is a reflection. When we do something like this, that's reflection over the y-axis, whereas if we do something like this instead, if we have a parent function f of x and h of x is negative f of x, well, that's just a regular old reflection over the x-axis, right? So all this is doing then, when we put a negative out here, you had the right description of what it was doing, Andy, but it just, maybe you didn't understand my question. I don't know, but I just wanted to know, without specifically talking about an exponential graph, that just reflects it over the y-axis, which does what you said. I mean, it's just going to tail off to the right. So that's what we get with an exponential function with a negative exponent. Okay, that makes sense. Maybe give me a 1 to 5 on that transformation stuff, on that reflection. Does that everybody get that? That makes sense. If I'm just going to replace an input variable with its opposite, then that always serves to reflect it over the y-axis. Okay, so then going back to Seth's observation earlier, yeah, this is going to be fine, isn't it? There's no value. If I look at this exponential function that we just created, yeah, the domain is all reals, isn't it? Right? So if the domain is all reals for the exponential function, and it's obviously all reals for x squared and plus 5, then we got no problems, right? So the domain is all reals. Okay? Any symmetry here? What do you think? We probably have to run the test, don't we? Test for symmetry. So let's see what happens. Our test for symmetry is just to evaluate our function at negative x and see what happens. So what is f of negative x here? Let's see what we get. That's going to give us negative x squared is the same as x squared, but then I'm getting e to the negative 2 times negative x. I'm getting e to the 2x plus 5. Okay, that's not, everybody agree? That's neither f of x nor negative f of x, right? So there's no symmetry here. That is not equal to f of x, and it's not equal to the opposite of f of x. So we've got no symmetry. Okay? That would have helped. That always helps. We can fill in some blanks for free then in our table, but we're stuck. All right, so we got to do some calculus. We got to take some derivatives. First derivative. What's our first derivative going to be here? Miss House, help us out.
Do you have to use the product rule or no?
We do, don't we? We got a product of x squared times e to the negative 2x.
So x squared times negative 2xe. I don't actually know.
Okay, so remember the derivative, let's remind ourselves about this one. The derivative,
Wasn't just the same?
yeah, it is. The derivative with respect to x of e to the u is just e to the u times u prime, right?
So e to the negative 2x times negative 2.
There you go. So negative 2 e to the negative 2x. Good. Plus e to the negative 2x times
Yeah.
2x. Good. Okay. So we could clean that up a little bit, couldn't we? We could factor out, it looks like how about if we factor out a 2x e to the negative 2x? And that leaves us with 1, right, from over here, minus, we got a negative there, minus x. Everybody buy that? that make sense? Give me 1 to 5 on that. Okay, so we got a factor. That's good. So let's talk about critical numbers for the first derivative. Are there any places where the first derivative is undefined? Yes or no? That's right. No. How come? Because there's no place that causes any problems, right? If I've got a product, look at all these factors that I've got. I'm multiplying here. I've got 2x times this factor times this factor. None of those individual factors have any problems, so why would their product, right? 2x is defined everywhere. E to the negative 2x is defined everywhere, like we previously discussed, and 1 minus x is defined everywhere. So we can say with confidence that f prime is nowhere undefined. Okay, where does our derivative equal 0?
At 1.
At 1? Anyplace else?
I'm not sure.
How about that factor right there? Right, if I were to set my derivative equal to 0, think what I just did there. I set 2x times, I'm gonna divide it into a bunch of factors. By the zero product property, right, the product of that factor times that factor times that factor would equal 0 when that one equals 0. That's right. Sorry, that one equals x equals 1, which is when that factor equals 0. Any others? Well, we know this one never equals 0, does it? If we look back at the previous page, this e to the negative 2x is asymptotic. It never gets down to 0. So that one never gives us a 0. But when does 2x equal 0? When x equals what? Okay, you said 0, right? Yeah, good. So we're getting two results here. Either x equals 1 or x equals 0. Okay? All right, so let's move on. Let's take a second derivative. So how do we want to do this? Let's go ahead. I mean, honestly, I would probably just differentiate this top one up here instead of having to do all these products, right? So why don't we, it's not a huge crime if you don't differentiate that first row, but I think that's what I would do. I'm going to rewrite this here as negative 2 x squared e to the negative 2x plus 2x e to the negative 2x. Now look at this. We can kind of cheat a little bit here, can't we? Because we've already done this derivative up here, didn't we? Isn't the derivative of f of x the very same thing as that derivative right there? Because the derivative of 5 is 0. Everybody see that? So we already did all the work, right? We already did all the work of differentiating that part in the, whatever that is, magenta box there, right? So when we differentiate now, we already know that I'm going to get negative 2 times the derivative of that, which is all that stuff right up there, okay? Which is a negative 2, I'll just kind of clean this up, negative 2x squared e to the minus 2x plus 2x e to the minus 2x plus, now I've got to differentiate that part right there, don't I? Okay. So we'll just do the same thing that we did the first time. We're going to use the product rule, aren't we? So we're going to get 2x times the derivative of e to the negative 2x, which was just that stuff right there. We already did that work, didn't we? We'll recycle it here. Plus e to the negative 2x times the derivative of 2x, which is 2. Okay, so there's our second derivative. Let's clean this up here. So if I distribute my negative 2, I'm going to get a 4x squared e to the negative 2x minus 4x e to the negative 2x minus 4x e to the negative 2x plus 2 e to the negative 2x. And I could combine, these are like terms, aren't they? I could combine those. So I get 4x squared e to the negative 2x minus 8x e to the negative 2x plus 2 e to the negative 2x. And now I could factor out a 2 e to the negative 2x. And what's left behind? So I'm getting 2x squared right, minus 4x plus 1. It's a lot of work, right? But we got it whittled down to something we can deal with now. So second derivative, where are the zeros of the second derivative? Well, we know that this first factor is never equal to 0, but maybe we could find zeros of this one, right? So we know second derivative equals 0 when we solve that we get solutions to this quadratic equation, when this quadratic expression 2x squared minus 4x plus 1 equals 0. Okay, does that have real solutions, first of all? Yes or no? Does that have real solutions?
No.
How come?
I mean, you could put it into the quadratic function that I forgot the determinant or whatever.
Discriminant?
But, yeah, if you do the first step to the first bottoms up method, you'll get x squared minus 4x plus 2, and there's no numbers that can ever add to negative 4 and multiply to 2.
Okay.
You're just done right there.
Okay, right. But all that's telling us is it doesn't factor conveniently, right? Just because bottoms up doesn't work, because this thing doesn't factor conveniently, doesn't mean it doesn't have real zeros, right? So we should just be able to evaluate the sign of the discriminant here. What's the sign? Let's just look at b squared minus 4ac for a second. This is a really, and this is, this is great prep for you guys, like for SATs and things too, because it's ACTs and SAT, because there's so much of this kind of stuff on there, right? So the discriminant, b squared minus 4ac, is that going to be positive or negative or 0 on this? Well, b squared is 16, right? Minus 4 times 2 times 1. Well, that's positive. So we do get two real solutions on this, don't we? So then we have to go through the hassle of probably using the quadratic. We're either going to complete the square or use the quadratic formula on this one, right? Take your pick. Probably quadratic formula, I guess. I mean, they're about the same, but if we use the quadratic formula, what are we going to get here then? X equals negative b, so positive 4, plus or minus the square root of the discriminant. So 16 minus 4 times 2 times 1, all divided by 2a, so 4. So we're getting 4 over 4 is 1 plus or minus the square root of 8 over 4. So that's 2 radical 2 over 4 would be the square root of 2 over 2, right? So we do get 2 critical numbers then. We know that the second derivative equals 0 at these 2 places. I mean, I shouldn't call them critical numbers. Those are zeros of the second derivative that we'll put into our table, right? Okay, well, true to form in calculus, we got through about a problem and a half in an entire period. So we'll just pick this one up next time. So where this is going to go from here, you can finish up. I extended the deadline a little bit on that, on the last concavity assignment. But honestly, our next section is just more of the same. We're just going to look at we're going to really hit these tables hard. So I'm going to give you another assignment or two on just doing more tables with some different kinds of functions. And for the next several times we meet, we're just going to keep cranking through this stuff so you can see some examples and kind of absorb how you think about this stuff and then practice on your own. Okay, have a great day. I'm here after school. I will see you. If I don't see you then, I'll see you on Friday.